Hi, and welcome back to my channel. So I decided to wear a jacket today just because it's cooler weather, it's a little bit colder in the house, and yeah, it was the last time I had to wear a suit jacket, or a blazer, really. I mean, truth is, even at my interview, I almost didn't wear it, because my job was in Tampa, and so it was really warm anyway. And yeah, I mean, like, you might even be, among mathematicians, I mean, a suit jacket might even be overdressed. Certainly no tie, not for a math interview at least. So today I want to talk to you about homework 2. This is for my numerical analysis class. Well, homework 2, I mean, really, I think this is like homework 5 or 4, but it's homework for exam 2. And so this was like a whole bunch of problems I gave you guys a couple weeks ago to go through. Today I'm also going to add a couple of more problems for you guys, just out of the initial value problems section, so covering Picard iteration and also Euler's method. I have a video I'm going to post later, maybe this week, just so you can see it. I'm not going to test you on it, obviously, because we're past the end of classes. But also I want to include some stuff on the Runge-Kutta method. Runge-Kutta method. And yeah, I had already recorded it, but I haven't really been too happy with how that turned out, so I want to go back and redo it. So look out for that. It's just something that is good to know if you're ever going to employ a numerical method to solve an initial value problem. You should probably use Runge-Kutta. But Euler's method is a nice, easy place to start, just to sort of get ideas of how things work. But that's not what we're talking about today. So here in this video, I'm going to cover the first half of the homework. And so the homework itself starts here. Let me just go ahead and start screen recording. Okay, there we go. All right, so the homework here, it starts with Newton's method. And Newton's method is really a way of finding a root for a nonlinear equation. And so we saw it being employed to find square roots and things like that. And so for instance, the first problem there asks you to use Newton's method on f of x equal to x squared minus 6. And so this guy right here. And yeah, so the ultimate result is that you should get the square root of 6 if you start at p not being equal to 1. So that's just a straight application of it. And then here we are asking you to find Newton's method for something that's a little bit more general. So here it's not just a polynomial, but it's actually a polynomial minus cosine. So that's going to be something that you won't really be able to do by hand. So you should probably use MATLAB. And then the question that's really important here is, could we use p naught equal to 0 for our guess? And yeah, you could try, but there's a real problem there, and just, I guess we can talk about that in a second. We'll go into a proper whiteboard discussion here in a second. I just want to talk about these problems. The third one, Newton's method to approximate within 10 to the minus 4 the value produces a point on the graph of y equals x squared that's closest to 0, 1. So this gives you a problem where, I think this is actually straight out of calculus 2, by the way, or calculus 1. In optimization problems, you would set this sort of problem up, and then you'd set it equal to 0, and then you solve for the 0. And in this case, we just want to use Newton's method in order to find that 0. So yeah. So we'll go ahead and play with that. Seems kind of off for the Newton's method. We'll see what comes up when I try it out, and maybe that sits better with a gradient descent method, but whatever. So Newton's method to approximate, same thing with this guy. So we're going to try that one. And yeah, good. And then the last one is to use Newton's method to obtain an estimate for pi using the root of cosine of x with a starting value of x equals 1. And how many iterations before you obtain the first 5 decimals of pi. So this one's sort of a fun one. So yeah, I'm saying to use Newton's method to find pi, but cosine of pi is actually -1. It's not 0. So what we're going to be doing is we're going to be using Newton's method, and it's going to find a root. What is the first root that we're going to find there? Well, that is going to be pi over 2. So if you're using pi over 2 to find an estimate of pi, you multiply by 2. And so every time we find an estimate for pi, or for the root, we can take that, set it aside, multiply it by 2 and see how close we got, and then go back and use the original root to do the next iteration. And so honestly, if you are in taking analysis or intermediate analysis, or say Rudin level analysis, it's interesting because you can start by defining your trigonometric functions in terms of power series, and so without knowing any geometry, you can define cosine and sine with power series, and then you just define pi as the root, the first root of cosine times 2, and so then that's that's actually sort of what that's getting at. And so if you were to define pi this way, then that's what you get. You could get it using power series. Sorry, notification just threw me off here. Yeah, okay. And then today I also want to talk about the differentiation and integration homework. And so here we have just numerical differentiation going on through here. We have several methods that we have concocted already, and some of them are sort of represented here. These are just using sort of Calc 1 notions of differentiability. And so we can go through here and we can compute f prime, but we'll have to notice that you can't use f of x minus f of x minus h here on the first line because there's no previous h to compare with. And same thing on the other side, you can't start here and then use this formula because there's no next h. And so so you'll have to use, for the two different endpoints, you'll have to use one or the other of these. And the middle one, you can do any of them that you want. But we know from experience in the lecture that if you use a symmetric difference, you actually get closer. So so really you shouldn't use x here, but you should use x minus h and x plus h. So x plus h, f of x plus h minus f of x minus h divided by 2h, and that'll give you a better estimate of the derivative using this data. And so for the middle one, you can actually get it even better than what you usually would. And that's exactly what the third item is for. And yeah, so here, the first one, we use forward differences and backwards differences to compute those derivatives. Ditto here, and then we use the symmetric difference for the middle points and all of those, and just sort of see like how different those answers are. That we don't really have we don't know what f is, and so it could be anything. And so so there we'll just have to just see how different each of these answers can be. Okay, so now here they actually give us the functions, and so then we're going to compute the error bounds. We've already talked about how to do the error bounds in the lecture itself, and that's just like what we did with polynomial interpolation. So we're going to have a formula that we need to memorize in order to compute, in order to estimate the errors for differentiation, and so we can go back over that. And then this one is going to be a little bit more involved. Maybe this will take another video just to go through. It's not something I would ask you to do to this extent on the exam. So you'd probably be asked to do it for maybe a second order or something like that on the exam to derive that formula, which you already have for the symmetric and differences and etc. But yeah, but here this is just to really so you can go and like test it out and see what you get. Yeah, so I guess actually this is probably a good stopping point for this video, and next time we'll talk about the numerical integration routines, and I'll try to get that video up either today, or either I'll try to record that again today if I have enough time, or I'll do it tomorrow. But yeah, okay, so that's what we get, and yeah, so I might as well go into the whiteboard stuff. Some of this stuff is gonna have to use MATLAB, so 10 to the minus 4 and 10 to the minus 4 here are both things that are really gonna have to use MATLAB to do, and also we're probably gonna have to use MATLAB to do this for cosine of x, and so you should be you can't use MATLAB on the exam, you can't use a calculator on the exam, so if I was going to give you a problem like this, it should be something that you can do by hand, or I'll ask you to do maybe the first or second iteration of it, but I won't expect you to be able to do it like for 20 iterations or get down to 10 to the minus 4. You should know how to do the algorithms. You should know how to do them by hand. And then some of the rest, but for this homework, some of this we actually have to just go ahead and take and use a computer in order to actually resolve it according to these specifications. These are clearly doable by hand, and yeah. Okay, so I think I'm going to stop this part here, and we can go ahead and jump into MATLAB and the whiteboard lecture and all that good stuff. All right, thanks for listening to me, and I'll see you in a second. Newton's method. Trying a nice fat pencil just to see if that'll clear things up. All right, take off my jacket because it's a little too cumbersome to write with it. Okay, so it's a little bit better. All right, so we're going to go over Newton's method, and so then the first two problems I said you can do by hand in the notes for the homework itself. So I might as well go ahead and give that a shot. And so the first one is f of x is equal to x squared minus 6. And they tell us to start with an initial point x naught, or they label it p naught here, as being 1. Now we know that here f of x equals 0 means that we have x squared minus 6 to be equal to 0, which then means that x must be equal to plus or minus square root of 6. And if we're starting with x equals 1, then we should converge to the positive root. So what they ask us to do is they want us to use Newton's method to find P2. And so what we're looking for is, so we want to find, say, we'll just say x2. So if you remember, xn plus 1 should be equal to xn, I think is minus f of xn divided by f prime of xn. And if you can't remember, you can do this through, this should all come down to a linearization. But yeah, we can go ahead and use this formula. So, so now if we go ahead and we, so what we need to do is we need to find f, which we have, but we need to find f prime. So we have that f prime of x should then be equal to 2x, right? Okay, so if I take a look at this, so then I see that x1 should be equal to 1 minus f at 1 divided by f prime at 1. And so this is going to give us 1 minus f at 1. And so that's going to be 1 minus 6 divided by f prime at 1, and that's going to be 2. And so looking at this all together, we have 1 minus negative 5 divided by 2 is 1 plus 2.5, and so that tells us that x1 should then be equal to 3.5. I think. Yeah, that seems about right. Is that square root of 6? No, not even. That's still a bit far. What that actually is we know that, you know, square root of 9, for instance, is 3. So this has to be closer to something like the square root of 10, 11, something like that. It has to be less than 16, though. So, all right, so now we hope we can use this 3.5 value in order to get a better estimate. So let's go ahead and take a look. And so we see that x2 then should be equal to 3.5 minus f at 3.5 divided by f prime at 3.5. So I could go ahead and just compute f of 3.5, f prime of 3.5, but we can maybe do this a little bit smarter. I don't know. So we have 3.5 minus, let's see, it's going to be 3.5 squared minus 6 divided by 2 times 3.5. And yeah, is that... it's not looking good. I was thinking you could probably cancel these guys if you separate them out. Let's see. So you get 3.5 minus, and now let's do two things. So we have 3.5 divided by 2 minus 6 divided by 2 times 3.5, and I'll just put that as 7. So maybe that does give us a little bit of a break. So let's see, keeping this going, we get 3.5 minus 3.5 over 2, so that is going to leave us with 1/2 of 3.5, so it's going to be 1.25, sorry, 1.75. And then we have plus 6 divided by 7. What is 6 divided by 7? Well, let's go back to the 4th grade. So we have 6 divided by 7, 6, 0, so 7 goes into 60, 8 times? Like 56, right? So, so I'm going to put 8, so 0.8, and so 5.6, that's going to leave us with 4, drop down another 0, and then what do we get now? It's going to be 7 goes into 40 5 times. It says 3, 5, and yeah, we could keep going, but I mean, I don't really feel like doing more. Okay, we'll do one more. So 50 is the next one, and so then that's going to be 8, and it's going to be 5, 8, 5, so 8, 5 bar. So it's going to be 1.75 plus 0.85 bar, and yeah, so let's see, what's that going to give us? So it's going to be 1.75. Okay, so it's going to leave us with a 0 after the addition of the 5, which is going to go put a 1 up here, so it's going to be 9, 7 plus 9, that's what, 6, so it's going to be 6, so then it's going to put a 1 up here, so 2.6085 bar. Right, so that's what we get. And yeah, so there you go. That's P2, X2, whatever you want to call it. And not too bad to compute. Yeah, just took a little bit of recalling long division. All right, so what is the next problem? So this is problem 1. If we take a look at problem number 2, they're telling us to go ahead and do the computation for f of x is equal to negative x cubed minus cosine of x, and starting at x of 0 is equal to negative 1. And we want to use Newton's method to find x2. All right, so again, same process. We know that xn plus 1 is equal to xn minus f of xn divided by f prime of xn. And then, so it means we need to find f prime of x is then equal to 3x squared, minus 3x squared, sorry, minus 3x squared, and then we're going to have plus sine of x. Okay, so this is actually one that you can't really do by hand, and yeah, so you know, you can go ahead and try. So I mean, for instance, starting at if we start with x of 0 is equal to negative 1, we're going to have x of 1 is equal to negative 1 minus f at negative 1 divided by f prime at negative 1. So that's negative 1 minus, and now up here we have minus 3 plus, we get plus 1 because negative 1 cubed is negative 1, and then we get minus cosine of negative 1, which is same as cosine of 1. And then we divide this by, say, minus 3 plus sine of negative 1, right? And so that's not something we can really compute by hand, and so this is something you might want to just try with a calculator handy. I don't have one handy at the moment, but I mean, that's a lie. I do, but I really don't feel like pulling it out and wrestling with it. I mean, you guys can plug this in yourself. This isn't the sort of thing I would ask you to do on the exam. This is something you can just go ahead and plug it in. They'll give you your first value, and then you just find x2 just by doing the same formula. So this is maybe a little even too simple for me to just go over. Okay, so what's the next thing that they asked? They asked, here's the important part of the question: could x naught equal 0 be used? And the answer is no. And the reason why is because we have f prime of xn, and if you look at, we have that f prime of 0 should be equal to minus 3 times 0 squared plus sine of 0, which is equal to 0, right? And so we have a divide by 0 problem. Graphically, what this manifests as is basically we're going to be what cosine of 0 is 1, and so we're going to be -1. So it's basically going to start at, say, -1 here. I don't know what it looks like otherwise. Okay, that's a lie. I do know what it looks like otherwise. I think it looks something like this. And so then basically what we're going to be using is we're going to be we have a flat tangent, and so the idea is that you'd be trying to find the 0 of that line, but there is none because it's horizontal. Because it's a horizontal line. So graphically that's why it doesn't work. Analytically, it's because we have a divide by 0 formula. Okay, not too bad. So now let's take a look at number 3. Now I'm not going to go ahead and do it exactly, but I'll tell it, because I mean this requires a computer, but I will tell you how to do it, and we can take a look at MATLAB, see if it can help us. So what are we looking for? We want to use Newton's method to approximate within, say, 10 to the -4, the value of x, the value of x that produces the point on the graph y equals x squared to closest to 1, 0. So let's just take a look at this graph to see what we're talking about. And if you remember, this is actually really close to some problems out of James Stewart. I mean, I know most of you guys probably took a calculus class that used James Stewart because it's the most popular textbook. And so if you take a look at this, the point at 1, 0, so we're looking at the point 1, 0. So 1 is for x, and 0 is for y. So we're looking at this. And so we're trying to use Newton's method in order to approximate the point closest to the graph here. So I mean, basically what we're going to look for is, we're looking at sort of this distance function here. So d of x, and we want to find the minimum of dx. So I mean, technically what the best way to go about this would be to use the gradient descent method. That would more or less work out. What we would do then is we would just take unit step sizes. But in this case, we're going to do something a little different. So what is the minimum of d of x? The minimum of d of x also makes d prime of x equal to 0. And it turns out that this point is unique. So there's only one point where this would actually end up happening. So then what we're going to do is we're going to take a look at this quantity, and we're going to try to solve this equation, which means we're going to need the second derivative. So let's go ahead and set up the equation. So we have the equation y equals x. We want the distance formula from 1, 0, right? So d of x then should be equal to x minus 1 squared plus y minus 0 squared. And if we want, the minimum is actually going to be the same if we even take out square root. So this will save us a little bit of a headache. And so, and we're not asking what the distance is, we're asking to find the x value that gives us the minimum distance. So I can just kill this and it'll be the same minimum. So now what I can do is I can go ahead and take a look at, say, x minus 1 squared, and we want this in terms of x. Y is implicitly in terms of x. So we have x squared minus 0 squared. Okay, so this gives us a formula of x minus 1 squared plus
x to the fourth. Now, let's go ahead and take a look at the derivative. D prime of x is going to be 2 times x minus 1 plus 4 times x cubed. And now what we want is we want to use Newton's method to find d prime of x equal to 0, right? So just got to pick something. And so I'm going to go ahead and pick x equals 1. So our initial guess, I'm going to say x naught is equal to 1. And then that means that xn, or xn plus 1, is going to be, say, xn minus, here we have d prime of xn divided by d double prime of xn, right? Using d prime as our substitute for f last time. So, yeah, so that's not too bad. I can go ahead and plug that in. So it tells us xn minus is going to be 2xn minus 1 plus 4xn cubed divided by this derivative of that. So it was d double prime of x. That's going to give me 2 plus 12x squared. So I'll put that on the bottom. Okay, and that should be xn. All right, so there you go. What is, and so then, you can just go ahead and compute, say, what is x1? And so if I use x naught as being 1, then it's going to be 1 minus d prime of 1 divided by d double prime of 1. And it's going to be 1 minus 2 times 0 plus 4 divided by 2 plus 12 times 1. Right, and so that gives us 1 minus 4 divided by 14, and so that is 1 minus 2 over 7, and yeah, you can go ahead and compute that. Well, I mean, we can just write a fraction at least. So it's going to be 7, so it's going to be 5/7. And okay, so we can go ahead and not be lazy and actually just figure out what this is. So back to grade school. So we have 5.0 divided by 7. 7 goes in 5. So 49, so 7 times. And so then that's going to be so we have 4.9, leaves us with a 1, puts a 0 there, 7, 1. And so yeah, so I'll say it's going to be about 0.71 for our first guess. And then x2 uses 0.71 minus d prime of 0.71 divided by d double prime of 0.71, and etc. But truly, if you want to get down to 10 to the minus 4 accuracy, you better use MATLAB. So that's how you do that sort of problem, and so that's not too bad. The next one is 5, and problem 5 says to use Newton's method to find an estimate for pi by using cosine. So find pi using Newton's method plus cosine. All right, so we're starting off with f of x is equal to cosine of x. And we just take a look at the graph. We end up getting, cosine does this, and so we see it's going to hit us at pi over 2. Right, and so we're going to use, initially, say, x naught is equal to 1. Or, you're going to put this into a computer anyway. But another thing we could use is maybe just pi over 4, because that's something we can actually calculate. So I'm just going to cheat and do this one. So then what do you get? So we have x1 is going to be, say, pi over 4 minus, say, f of pi over 4 divided by f prime of pi over 4. And so it's going to be pi over 4 minus cosine, which is going to be root 2 over 2, divided by the derivative of cosine, which is minus sine of pi over 4. So this gives you minus root 2 over 2. And so that tells us then that it's going to be pi over 4 plus 1. And so then so that tells us our first guess for the root is pi over 4 plus 1, which is say pi plus 4 over 4 if you like. Now, of course, here I'm using pi as my guess, and so that's sort of cheating in here. And so this should get me closer to pi over 2 is the idea. And so this should, in some weird world, my pencil is dead now. But in some weird world, that should get you pi over 2. And then the idea is that, is that going to charge it? There we go. So then the idea is that this should be equal to roughly pi over 2. And then to get an estimate for pi, we compute, say, 2 times xn, right? And then that's going to give us our estimates for pi. Of course, you don't use 2xn and feed it back in. You use xn to feed it back in, just like you do the algorithm anyway. And so here I use pi over 4 as my initial guess, but again, we don't even know what pi is in this theoretical world. And so I just start using x naught equals 1, plug that into MATLAB. That's a much more realistic situation. Although in a much more realistic situation, you just use Archimedes' formula or one of the other many formulas for pi. But this is sort of a way you can use Newton's method to find the answer. Okay, so that's all the Newton's method homework problems. And so the next bit that I want to talk about are these differentiation and integration routines. And so these are going to use the material from that lecture. Okay, so I took a brief break to give my pencil a little TLC and charge it up. Sounds like my cat is going off right now. Maybe he needs a little TLC too, but right now I have to do work. So now we're going to move on to the problems for differentiation, and we'll cover the integration later. So I think that is like the worst handwriting I've ever had. Actually, you guys probably seen worse. But yeah. So now let's go and take a look at problems 1 and 2. Honestly, I'm just going to go ahead and do 1A, and everything else works exactly the same. So we have 2 different formulas here. So we have formulas, we have forward difference, and we have backwards difference. And then we have symmetric. All right, so the symmetric comes up in part 3. And so if you take a look at the forward difference, it's f prime of x, and we're going to use f of x plus h minus f of x divided by h. Here we're using f prime of x as it should be approximately equal to f of x minus f of x minus h divided by negative h. And then the symmetric one tells us that f prime of x should be equal to roughly f of x minus h plus h minus f of x minus h divided by 2h. And so presumably if we can do this one, we should, because in our lecture we saw that the error is a little bit better. But you don't always have that option, and you can see that here. So if we take a look at say 1 and A, they give us this table. And so they tell us I want x, we have f of x, and then the question is, what is f prime of x? And they give us several significant values, so 0.5, 0.6, and 0.7 for these guys, so our h is going to be 0.1. And, and here we have 0.4794, and we have 0.5646, and then we have 0.6442. A little sore throat today. Hopefully it's nothing serious.
can't even a little cough, you always wonder. It's like, is this COVID? Is this, am I going to get really, really bad? Or is this just a silly little cough? It's probably a silly little cough, and I'll put off panicking for later. Anyway, so we need to estimate these values. So if you look at what we have here, we want to use forward difference, backwards difference, etc. So we have these options. So we have f of x plus h minus f of x divided by h, and we have f of x minus f of x minus h divided by h. And we want to fill in these spots here. Now, for this point, it doesn't matter which one you use. You can use either one of them, and ultimately you should really just use the symmetric difference. But for this one, it does matter, because we can't use this formula because there is no x minus h. We don't have a value at 0.4. So we have to use the forward difference. And for this one, we have to use the backwards difference because we don't know what 0.8, the value for 0.8 is. And so then that's what we're going to do. So we say for the first entry, we're going to have f prime at 0.5 is roughly equal to f of 0.6 minus f of 0.5 divided by 0.1, right? And so what is, and that should be minus h here. So what is this value? So 0.6 is going to give us 0.5646 minus f of 0.5, so it's going to be 0.4794 divided by 0.1. And so what we're going to get is, so we get like 0. Well, might as well actually work it out. So in this class, you didn't think you'd be doing this much arithmetic, huh? So 0.5646 minus 0.4794. So that should give us 2. 6 cancels that, gives us a 1 here. And so that's going to be 5 here. It's going to be 5 minus 7. So it's going to be, so we're going to cancel one of these guys and put a 1 up here. So it's going to be 15 minus 7. And that's going to give us 8. And then we have a 4, and so 0. There you go. So that is the difference between those two guys. And then divided by 0.1 means we multiply it by 10. So the derivative is going to be about 0.852. So that's what I'll put here, 0.852. And then you go on to the next one. And so you can use either one of the methods if you want, or you can use symmetric difference. Like I said, in this part, I wanted to use the left or right, or the forward or backwards difference. But honestly, let's just use symmetric difference just to save us some time. It should be more accurate anyway. So f prime of 0.6 we can then estimate as f of 0.7 minus f of 0.5 divided by 0.2. And so what are these values going to be? So we are now taking 0.6442 minus 0.4794. And so then let me switch to a slightly smaller pencil. So this one is going to cancel, put 1 here. It's going to give us an 8 here. It gives us 3. 3 minus 9, can't do that, so cancel that 1. So we get 13 minus 9, that's going to give us 4. And so 3 minus 7, can't do that, so it's going to be 5, 13 again, and that's going to be 6. And then we have 5 minus 4, 1, so 0.148. So let's go back to our fat marker. So there's 0.1648, right? And so that's what we have here. And so that goes in for this middle guy, 0.1648. Oh, sorry, not quite. Divided by 0.2. And so divided by 2 is going to give us 0.0824. And then divided by 0.1, so that's going to give us 0.824. All right, so that first value I wrote there was significantly different than the neighboring one, so it include me in that. Maybe it should be a little different. So 824. So that's what we got. All right, so now the last one is f prime at 0.7. Now this should be equal to roughly
f of 0.7, minus f at 0.6 divided by minus h. So h is 0.1. Okay, right. Yeah, all right. And so going ahead and computing this, what are we going to get? So, okay, so if we take a look at this, we have, let's see, so f of 7 is going to be 0.642, and minusing 0.5646 divided by minus 0.1. Just thinking for a second. I think this should actually just be positive, because we're really looking at the difference between x minus h, I'm sorry. So just give us h. So I think it was poor transcription on my part. So let's put a positive on these guys. All right, that makes a lot more sense now. Okay, so going back through here, I mean, honestly, I'm getting tired of writing this stuff out. 0.6442 minus 0.5646, and so switching to small pencil, we get putting 1 up here, this leaves a 6, this leaves 3, put 1 up here, that leaves a 9, then we have 3 up here, slash this one, this gives us a 5, a 3, and that gives us a 7, and then 5 minus 5, 0. So 0.796, and so I divide that by 0.1, multiplies by 10, and so it's going to give us 0.796. So I'll put here 796. Okay, so there, completed the table. And so here we used forward difference, backwards difference, and symmetric. Okay, so there you go. These are the answers you were looking for. Now, if I tell you to use a particular method, say the forward difference or backwards difference, just make sure you actually employ that. Okay, so yeah, let's move on to so that's 1, 2, and 3. I mean, they're all roughly the same, and I use the symmetric difference on the middle one. So in 4, they're telling us that the exercise we're taking from in exercise 1, we're taking from the following functions. And so here, if you take a look at 4a, it tells us that this guy came from f of x equals to sine of x. They want to compute the actual errors using the error formulas. So find error bounds. Using formulas. Okay. So there's another one. They have e to the x for the part B. They have an exponential minus polynomial, and looks like we have, and for problem 5 we have similar sort of things. So here we need to use error formulas, and so I'll just do it for the forward difference. And so if you remember, we had the error formulas as Rn of x was equal to x minus x1, product all the way up to x minus xn plus 1. And then we had f of n plus 1 xc divided by n plus 1 factorial. So if we want to take the derivative, if we want to find the error committed by the derivative, we need to take the derivative of this. And so, and in this case, we're just choosing x1 is going to be x plus h, and x2 is going to be, say, just x. And so, plugging that in, we see that, say, we have r of, say, 1 of x is going to be I should say x naught, just so we keep track of this. So it's going to be x minus x naught plus h. I didn't want to confuse with that x. And then we're going to have x minus x naught. And then we have here, we're only care about the second derivative, right? So f double prime xc divided by 2 factorial. Okay, so if I take the derivative of this guy, it's going to be r1 prime of x, and so then it's going to be the derivative with respect to x, so we only have, so basically it's going to be the product rule. Derivative of this guy is 1, derivative of this guy is 1, and so it's going to end up giving us x minus x naught plus h plus x minus x naught, and then f double prime xc divided by 2 factorial. Now we have a clear bound on f double prime because f double prime of x is minus sine of x, right? And so so then we can just replace, we get a bound on this guy by 1. So we see that we have the absolute value of r prime sub 1 at x itself is bounded by the absolute value of x minus x naught plus h plus x minus x naught absolute value, and then all this guy divided by 2. Now so here for difference, if we take a look at the last slide, so let's just say we took 0.5, so then basically what we're going to have is x naught is equal to 0.5, and then we're also, and so we want r1 prime at 0.5, right? And this is what we're trying to compute. We're trying to get a bound on the error for this guy. So what I can do then is I can say, well, r1 prime at 0.5 is less than or equal to, and so on the top, x is going to be 0.5 and x naught is also 0.5, and so all that leaves up here is it leaves minus h out of that guy, and then the next part just ends up being 0 divided by 2. And so that tells us that the answer is going to be that this bound is, the error is bounded by h over 2, and so the error is bounded by say 0.05 because h was equal to 0.1. And there you go, and that's how you do that problem. So that's not too bad. And yeah. Now 6, I'm not going to go ahead and do 6. That would take way too long. Maybe I could do it in another video if you really want to see it. But the point is that you really just take, well, I can sketch out how you do it. Let's just do that. So 6, it says derive, and big O h to the 4 5-point formula to estimate f prime at x naught, right? That uses f of x naught minus h, f of x naught, f of x naught plus h, f of x naught plus 2h, and f of x naught plus 3h. And in here we're given this hint. It says consider the expression a f naught minus h plus b f naught plus h plus c f naught plus 2h, etc., and expand fourth order polynomials and choose a, b, and c appropriately. So that is one way you can do it, and that will give you an answer. But and certainly, yeah, I mean that would give you something. But I don't think that's really the best way to do it. I think the interpolation route is a much cleaner way of getting at this answer. But I mean, both ways are valid. I just wanted you to give it a shot, see if you can find it with the Taylor polynomials, and yeah. But what you can do instead, if you don't want to do that, is you can declare, say x1 should be x naught minus h, x2 should be x naught, x3 is x naught plus h, x4 is equal to x naught plus 2h, and x5 is equal to x naught plus 3h. And just like what we did before, you can use interpolating polynomials. And so we can interpolate f, say xi and f of xi with a polynomial. And then differentiate the polynomial. And that'll give you something. And I mean that might be the most straightforward way of going about this. And yeah, let's see if we can check out with the Taylor polynomial method though, just to do it. This is not looking fun. Okay, so let's take a look at it on a smaller scale, because we didn't really do a problem like this on the homework or in the lecture. But yeah, so let's consider these points: x naught plus h, let's say x naught minus h, x naught, and x naught plus h. Right, and so this should give us something like the symmetric difference formula. So if you take a look at, say, f of x naught minus h plus b of f of x naught plus h, what we end up getting is we see that f of x naught minus h should be equal to f of x naught plus h f of x naught prime plus, say, h squared at f of x naught double prime over 2, and should be not h, but should be minus h, so here will be a negative, here's a positive, and then you can keep expanding it if you wanted. And here we have f of x naught plus h is going to give us these other ones. So f of x naught plus f plus h f prime of x naught plus h squared f double prime of x naught over 2. And so what we're aiming for is we're trying to figure out what the heck this guy is. And so if I were to put a and b as so I'm trying to figure out how I can use these guys to basically get something that's approximately f prime of x naught times h, right? That's ultimately what we're trying to do. We could also throw in x naught if we want another parameter, but for now let's just see if we can use just these guys. And so ultimately I get a f of x naught minus h plus b times f of x naught plus h is equal to, so we're going to have a times f of x naught plus a or minus ah times f prime at x naught plus a h squared f double prime of x naught divided by 2. And now we're also adding on this term, so we have b f of x naught minus plus b h f prime of x naught plus b times h squared times f double prime of x naught over 2. Okay, so ultimately what we want is if we combine like terms, so f of x naught here, we want that to go away. We want only this term to really survive, so these guys. So we should want a plus b should be equal to 0. And then we want that these other terms, b minus a, coming from these two guys, that should be equal to 1. And the other one, whatever. Whatever is attached here, I don't care. because it's just going to be A and B when they're combined are just going to be constant, and then we're going to have some sort of h squared dependence here. And so then if you go ahead and you just try to solve it, then you see that we have that A should be equal to minus B, and then that means that we have, so B minus A is going to be 2B is equal to 1. So that tells us that B is equal to 1/2, which is equal to minus A, right? And so then that's what we get for those choices, and it should eliminate everything here except for this term, except for this extra term. It turns out, actually, if you look at this, those A and B are actually going to end up annihilating, but that's not quite true. I made a mistake when I was expanding this. We have C, we have one C here, and we have another C here, each one coming from the expansion. So this will be 1 and 2. And so this C1 is going to be between x minus h and x, and this C2 is going to be between x and x plus h. And so these two values aren't exactly the same. But what we do here, though, is we kill this term. And so that term goes away, and we're left with this guy is just being equal to 1, because b minus a is equal to 1, right? And so that tells us then that f of x naught minus h with a negative 1/2 plus 1/2 of f of x naught plus h is equal to h times f prime of x naught, and then plus some term that is big O of h squared. And so there you go. It turns out that this formula is exactly our symmetric difference formula that we had before. And so that's more or less what they want you to do here, except you just expand out into higher order polynomials for all these guys. And so you'll just have a huge system of equations to go ahead and work out. And so it might work out better than the interpolation, polynomial interpolation, but you should get roughly the same answer, and or at least a comparable answer. And so so it's a good practice to do. And so now you have another tool in your toolbox. Okay. So that actually covers everything, I think. So this looks like a good place to stop. And yeah, I don't think I'm going to go into doing. We already have the example code for doing MATLAB. This code, you just plug this formula into MATLAB and you should get the answer out that you want. This gives you a setup of how you need to do it, and so that should be enough for you guys. And so I might ask you to write the setup for this problem, but not actually. So find the d that you need to find, and then write down the formula for Newton's method. In terms of doing something like this. This is something I would expect on the exam. I would not expect you to actually execute it. Not more than just say one iteration. And then this one again. I just looking for you to recognize that twice of the roots that we're trying to estimate is actually pi. And so is actually our estimate for pi. And yeah, so I think it's mostly done. Let's see, was there anything else I wanted to go in here? Let's see. Oh, yeah, this was silly. This should be 7. Because, oh my god, I don't know why I did that. Yeah, so the first 2 digits here are fine. But yeah, the last one, yeah, okay. So minor error there. So scratch that. But everything else is fine. And get rid of the bar here. Okay, yeah, so a little arithmetic mistake, but at least I caught it before I ended the lecture. Anyway, yeah, so practice your arithmetic. Don't be like me, and go pull out your times tables from the 4th grade. And I guess it's a good place to stop. And yeah, I will go back to the office.
Okay, so I hope that clears up the first chunk of the homework. And so, yeah, that's Newton's method, differentiation, integration. Well, we didn't do integration, but we covered the differentiation problems for the most part. I left a couple there just because, you know, we only have so much time. And yeah, so I'll try to record another video pretty soon and get the rest of those problems out to you. And I'll also add a few problems for doing initial value problems using Picard iteration and then some problems out of Euler's method. These are going to be, say, differential equations level 1 sort of problems, and so yeah, so don't expect them to be too bad. I'm actually going to pull them straight out of Saf's differential equations book, Nagel, Saf, and Snyder. Anyway, yeah, so thanks for watching, and yeah, I'll see you next time.